give us a let that we may use that to excel in our exams, oh God. I thank you for your strength. I thank you for your love. And Lord, whatever they may be putting on the paper, oh God, open our brain cells that we can do whatever is on the paper and ask of us. I thank you for everything that you have done. As we may go into the lesson now, in your name I pray. Amen.
Amen. Thank you, Miss Leslie. Which school are you from?
Well, I'm an adult.
Oh,
Mhm.
my bad.
Mhm.
Okay. All right. So for somebody who's asking where is the YouTube channel, so it should be streaming on MOE Jamaica channel in a bit. All right. So students, colleagues, we want you to welcome our master teacher who will be taking us through this session, Mr. Imran Miller from, well, presently at Campion College, yes, former MC student, Monroe College. All right, so he is our facilitator for this session, and he will be taking us through as we prepare for our CSEC chemistry examinations. As we go through, remember, if you have a question or a comment, you can use the raise hand feature. Please mute all mics. If you raise your hand, we'll allow you to speak. All right. Any other questions or issues, you can just put in the chat. All right. Please respond to the questions posed by Mr. Miller. All right. It's your participation that will help you to do the very best that you can in this session. All right. Over to you, Mr. Miller.
Okay, good afternoon, everybody. Hope you are all doing well and hope you're all energized and focused for the exams that are coming up. Today, I am looking at going through two of the topics that we are told will be featured on the upcoming CSEC examinations. Those two topics that I'll be looking at are mole concept and electrochemistry, two crucial topics for sure. And look, I think that I know the reputation that certainly the mole concept holds among students. And indeed, the electrochemistry holds a similar kind of reputation as topics that students find difficult. But I believe that we can do well if we approach it correctly. And so today, what I will be doing is basically approaching the questions in a way that we can easily remember, easily understand, and hopefully to be able to reproduce a kind of performance in the exam. Now, I'm not telling you that this is a magician. I'm no magician. What I hope to do is to be able to fix or help you through some of the problems that you have by looking at some questions that will give you an idea of what you'll be expecting on the exams and give you practice. Okay. Now, what I'll be doing, because we only have 2 hours, there's no way you can teach either of these topics in 2 hours. So what I'll be doing is I'll be teaching and going through the theory at the same time. So when we come up on the questions, we'll do the theory, or I will do a quick little theory review before, and then we'll go into some questions. But each different type of question that we do the theory that comes with it, and we see how far we can go. I'm gonna try and do 1 hour on each, and we see where we go from there. Okay, so I'm gonna share with you now my screen. I'm going to just talk a little bit about the mole. All right, so, all right, who's going to tell me in the chat, what do you understand by the mole? Students, come on. Tell me what you understand by the mole. What do you understand by the mole? Do we have anybody writing in the chat? Yeah, we have some writers in the chat.
There's unit of measurement. That's the first one I'm seeing. Somebody says it's blind. I think they're talking about the animal.
Oh, it's right. Very smart. Very, very smart.
Amount of particles in a substance. From
Okay.
Peter Gay Campbell.
Interesting. Okay. All right. So I'll be also using a little tool for feedback apart from the chat called Peer Deck. But I think maybe since we're streaming and so many of you might be on the stream instead of on this, I think I'll probably lean on the chat some more. So I'll go back.
Okay, some more responses. Number of atoms in 12 grams of carbon 12, amount of particles in a substance compared to 12 grams of carbon 12.
Wow, okay. All right. Well, that's interesting. Are you seeing my picture here, the mole, the rat, on your screen? Yes?
Yes.
All right, good. All right. So I was gonna ask you, how do you feel about this topic? Are you fine with the mole? You find challenges? Does it make you a bit sad? Are you absolutely crushed by it? All right, let me see what you're saying in the comments there. I want to have a feel of how people feel about this topic.
Challenging, crushed, challenges.
All right.
I've seen a lot of crushed, man. Absolutely crushed. 2 out of 100. Somebody said clueless.
Wow. All right. Let's see if we can provide some light for you, or some lift off, some weight off you, as we go through this session. It's kind of important for you to understand a bit of a background to the mole. I hate when you just go into a definition. What does it mean? Why do we have the mole? What is the rationale? And the rationale for the mole is that we're trying to count particles that are very, very small and very, 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 very plentiful. Just say I could count 100 mangoes out there, right? I pick up 100 mangoes, I could count it, right? Guess how we find that, how we do that easier. We group them in dozen mangoes. And by saying 5 dozen, we're simplifying the counting by grouping it. It's the same idea with the moles, right? The mole. Because there are so many atoms, right, in just a small amount of material, it makes sense to group them in a bundle, right? So a mole is just a way of bundling particles into a unit that we can more easily deal with in terms of the numerals involved. All right. So let's look at it. So let's look at my screen here. All right. So what we're saying is that the atoms and particles are too small to keep track of, right? So we bundle them together. So a mole is a package of many particles, like atoms. All right. So how much exactly, right? Well, it's a big number. It's 6.02. I'm going to stop there, times 10 to the 23. All right. So it's 602 and then 21 zeros after that. It's a big number. All right. Now, I think that some students are a little bit intimidated by that number. And that number is known as Avogadro's number, Avogadro's constant. All right. Now, so 1 mole, here's the relationship that you want to remember, the first relationship. And here's the thing with studying moles. I'll give you this tip. The best thing to study moles, the best way to study moles is to study relationships and not formulae. You can study the formulae later, but learn the relationships first, because the relationship gives you the formulae. It's easier to remember the relationship and then derive the formula out of that. That makes life much easier for you. All right. So we're saying that 1 mole is the amount in 6.02 times 10 to the 23 representative particles. That's a very important term, representative particles, because some materials are made of atoms, molecules, or they can be made of formula units and ions, as in the case of ionic compounds, right? So depending on nature of the substance, right, their representative particles can be different, right? So let's say sodium chloride, for example. That's an ionic substance, table salt, right? Everybody knows that, right? That is an ionic substance. It is a formula unit NaCl, all right? So it has sodium and chloride ions. So we can represent it in terms of formula units to represent NaCl, or we can represent it in terms of ions. All right, so we have to be careful there, and we can talk about that later. But we're not going to do anything too complicated today. We want to get the basics right. Right. So there are so many particles. As I said, there's not one mole of people on Earth. There's many more moles. There's many less people on Earth than one mole. Right. So there's not one mole of pennies on Earth. There's not one mole of stars in the Milky Way. All right. So you see how big that number is in terms of that bond that we have to put the particles together, because there are so many particles.
Mr. Miller?
All right, yeah.
It seems if your connection keeps slowing down a bit, so probably if you take off the video, maybe it will help.
Okay. Let me take that off. All right, there you go. Yes, let's take that off. I hope that I'm not lagging behind. All right. Yes. So this is the first relationship that we want to focus on. 1 mole of anything. 1 mole of particles. In fact, 1 mole of anything is 6 times 10 to the 23 items, yeah, of the thing that you're talking about. All right. So 1 mole of sugar contains 6 times 10 to the 23 molecules. 1 mole of helium exists as atoms, no? Sugar exists as molecules. 1 mole of helium is 6 times 10 to the 23 atoms, because helium exists as atoms. So that's the first relationship I want us to remember. All right. Okay. All right. So continuing. All right. Now, here I have a little justification for the moles. I don't want to go into it too deep because I know we don't have a lot of time. But basically, one of the reasons why we have to bundle particles is that not only is it hard to quantify them in terms of numbers, but it's also hard to quantify them in terms of mass, because the particles are so very, very small, right? So what scientists did was they came up with an alternative system of weighing, so to speak, because the particles are so small, there's not one scale in the world that we could put one particle on and read off the weighing. All right, we get such masses by spectroscopic measurements, not by weighing on a scale. All right, so what they did is that they came up with a sort of new scale for comparing masses, right? And they call it relative mass scale. And they came up with this unit called AMU, atomic mass unit, right? And so what they did initially was that they assigned the lightest atom, which is hydrogen, a mass of 1 AMU, basically. And so you're the lightest one. We're going to compare everybody else to you. So you know what, magnesium, you look like you're 24 times heavier than hydrogen. So if hydrogen is 1 AMU, you know what, you're 24. Right? Carbon, you're 12 times heavier than hydrogen, then you're 12 AMU, okay? And basically, what the mole is that number which links that relative mass scale to absolute mass scale, to the absolute mass scale. So if I have 1 mole of anything, right, it's going to have the same mass in grams as its relative mass number, right? As its relative mass number. So what it means is that if I say carbon, for example, is 12 AMU in mass, 12 atomic mass unit. If I have 1 mole of carbon atoms, if I have a 1 mole bundle of carbon atoms and I put it on a scale, it's going to weigh 12 grams. All right? Yes, yes. And so that idea came up, gave us what we call molar mass. Molar mass. All right? I don't want to go too far into it without asking you a few questions. All right? So I am going to stop there, and I'm going to go back to what I started by saying, by defining the mole. And I want you to answer this in the chat if you can. All right? I want you to answer 2 examples here I have. The first one says, 3 moles of sodium has how many sodium atoms? Now remember now, this is asking you about the number of atoms and it gives you moles, right? And the relationship between mole and number of particles is given by here, this relationship here, 1 mole is equal to 6.02 times 10 to the 23 particles. Is anybody answering this question? Question 1.
Not yet.
How many atoms of sodium are there in 3 moles of sodium?
Okay, current students, post your answers in the chat.
You guys hearing me?
Yes, they're hearing. Okay, I'm seeing some answers now. So we have 1.8 times 10 to the 24, 1.806 times 10 to the 24. Yes, 1.81 times 10 to the 24. You're hearing that? Mr. Miller? Did we lose Mr. Miller? Okay, all right, that looks about right. I think we lost Mr. Miller. Just give him a second to get back on. Yes, 1.806 times 10 to the 24. All right, and of course, you would have calculated that by multiplying the 3 moles by Avogadro's number. Okay. I just give a minute. Let me see if I can get back Mr. Okay, he's back. Mr. Miller?
Yes, I'm back. Yes, yes. So what were the students saying?
Yes, they were given 1.8 times 10 to the 24th. I saw that was the most popular answer. There's a 3.6 times 10 to the 23rd. I'm not so sure which one that is related to. Oh yeah, okay, no, they're multiplying the 3 by the 6 by Avogadro's constant. Right, so it's 1.8 times 10 to the 24th power. That's what I'm seeing. And there's a 1.8 times 10 to the, well, this looks like 25. You're hearing? Yes, so you can respond.
Yes, yes. So folks, so what is very, very important is for the first things first, you need to learn to use your calculator, right? So for some people, how you put on your exponential with your calculator, it varies, right? Depending on the calculator, the brand calculator that you have. So the first thing you want to do is, in collaboration with your friend or your teacher, find out how your calculator works when you're doing exponential values, when you're calculating using exponential values, okay? That's very, very, very important, right? So we know that, okay, that 1 mole of anything, and this is sodium, has 6.02, right, times 10 to the 23. Now this sodium exists as atoms, yeah, it's a metal, All right, so we know that's going to be atoms. Yes, and the question is, if I have 3 moles of sodium, right? How many atoms? Since we don't know how many, we're going to say X. How many atoms are in that? And so we can just use our ratios to work that out. All right. I'm old school, so we say cross multiply. The mathematics people at MOE might be shrinking and wanting to give me a shake up. Right? But yes, so X would be equal to 3 times 6.02 times 10 to the 23. So all those people who were getting 1.8 times 10 to the 24, you're correct, right? 1.8 times 10 to the 24, but it's important to put your units. We are calculating atoms. Are we okay?
Right.
Yes. All right. So that is fine. And of course, they can do a little reversal of that. All right, by giving you the molecules and asking you for the moles. All right. So
okay. Somebody's asking about the person who got 25. Well, I guess the 10 to the 25.
10 to the 25, right. So that is probably due to the error that I was talking about. Yeah. How you do the exponential, because some of you will write times, if in some of the calculators, if you write it out like that, if you write out 6.02 times 10 to the 23, it actually multiplies by an extra 10, right? So depending on the calculator you have, you have to know exactly how you put in times 10 to the something, okay? Be careful, so you have to be careful with that, okay? For some calculators, you just press exponential and it multiplies, it automatically goes times 10 to the whatever, you just put into the number. But for some, you need to write out times 10 to whatever. So you have to know your calculator, all right? That's the best I can do for you there, all right? All right, so what I'm gonna do now, I'm gonna skip ahead a little bit. All right? Because I want to get to some of the questions that you look like on the exam, and we work the theory as we go. So don't worry about not knowing the fundamentals. All right. So as I said, the mole was also used because again we had a problem with mass and measuring mass. So 1 mole of a substance, as I said, if we put a 1 mole bundle of a substance, that gives us a significant weight that we can weigh on a scale, right? So that is how we came up with this idea, molar mass, right? The mass of 1 mole of a substance, right? Very, very simple. Molar means of the mole, and mass is mass. So it's mass of 1 mole, right? Literally. Of course, 1 mole contains a number of particles. So we have an alternative definition there, right? We have mass of 1 mole of a substance, or we have mass of substance which contains 6 times 10 to the 23 particles. I'm going to show you how we can use that in a second. All right. So let's just let's do this one quickly. Molar mass is mass of 1 mole. Very, very simple. So let's look at what this means for, say, magnesium. If we say the molar mass of magnesium is 24 grams per mole, mass per mole, mass of 1 mole. Get it? So that's grams, that's mass per mole. So that's the unit, right? This means that if I could count up 6 times 10 to the 23 atoms of magnesium and I put it on a scale, it would weigh 24 grams. That's what it means. All right, so answer me this now. What is the mass of half a mole of nitrogen molecules? Pick one before we go on.
So I'm seeing some 7 grams, 7G.
17. We're getting 17 as well?
No, I'm just seeing 7.
Lots of 7.
Yes, but you'll have to help them out here. I am even seeing 3.5.
Seeing 3.5 as well. This is interesting.
Very.
All right, so this is interesting. All right, so notice, guys, I give you here, N is equal to 14. What do you think this 14 means here? Everybody write in the chat, what does this 14 represent? What are they saying, camera? Okay,
Didn't
I see a
realize
number.
I was muted. So if somebody's
Okay.
saying RAM, atomic number, molecular mass, mass
Wow.
number, relative molecular mass.
Yes.
So you have some clarifications to do. Mass number,
okay.
MR.
All right. All right. So let's clear this. Let's clear this. All right. So when you see N equal 14, guys, what this means is the relative atomic mass, or you could say the mass number as well. Relative atomic mass, right, is equal to 14. All right. Relative atomic mass. All right. So if you look at your periodic table, you see nitrogen. You'll see a number 14 in the top left-hand corner. And you'll see a number 7 in the bottom left-hand corner, right? So your relative atomic mass is this number here, the one in the top left-hand corner. Okay, now that is giving you the relative mass of a nitrogen atom. That's the average mass of any given nitrogen atom out there. It's about 14, okay? It's not exactly 14. We can have that discussion later, or maybe with another presentation, but it's about, let's say it's 14. Now, this relative atomic mass, remember, the units for this is a fake unit that we call AMU. And remember, the AMU is just there, it's a relative mass unit. It's not really a true mass unit because it's just there to compare the mass of one atom to a standard. The standard nowadays is actually carbon. That's why we always, when we define relative mass, we say compared to the mass of 112, the mass of a carbon-12 atom. That's what one AMU is. But this now, relative atomic mass is the average mass of one atom. Now, let's go back to the question and read it carefully. Let's go back to the question and read it carefully. It says nitrogen molecules, doesn't it? Let's say nitrogen molecules. A nitrogen molecule is N2, 2 atoms together. So the mass of a nitrogen, the relative mass, and this would be the relative molecular mass because it's a molecule, would be 2 times 14. That would be 28. Now, so that's 28. Now hear this, guys. The relative mass is the same as the molar mass in terms of number. But of course, the molar mass speaks to the mass of a bundle of 1 mole, right? So that will be the same number, but the molar mass will have units of grams per mole because it's 1 mole put together, and you weigh it on a scale and it weighs that number, that mass. All right. So what we can deduce from N equal 14 and the fact that nitrogen is N2 is that the molar mass of N2 is equal to 28 grams per mole. All right?
Excuse me, sir.
Yes.
How did you get the 14?
All right, the 14 will be given to you. You get it from your periodic table by looking at the atomic symbol for nitrogen. Okay? And if they give you a question, chances are they'll give you that number, the relative atomic mass of the element.
Okay, sir.
All right, good. Okay. All right, so now that we know that because molar mass of nitrogen that's nitrogen gas, N2. Nitrogen exists as N2, by the way. So if they said nitrogen alone without saying molecules, you should assume that it's a molecule because that's what it exists as, right? What are the other atoms that exist? What are the other elements that exist naturally as the atomic molecules? You should know oxygen. You should know about hydrogen, right? You should know about all the halogens: fluorine, chlorine, bromine, right? Iodine, all of those exist as diatomic molecules. They expect you to know that, all right? Okay, all right. So if the molar mass is 28 grams per mole, that means that 1 mole of N2 weighs 28 grams. And the question asks, how much is half a mole? Right? So therefore, half a mole of nitrogen would contain, let's say, X. You'll notice, some of you might notice that I haven't used a formula yet. Don't like formula. Formula come last.
Just reasoning.
Right? Right. We're reasoning it out. We're doing relationships and remembering definitions. All right? So 1 mole of N2 weighs 28 grams. So 0.5 mole of N2 is it's just half of that, right? Half of 28, right? Which is 14 grams.
All right, seen some 14.
All right, so we're getting there. All right, 14 grams. This is your answer, guys. All right, good. All right, so we're getting there now. We want to get through this first part of moles. All right, so then let's go. All right, so we're gonna start new share. Let's go back. All right, so let's gonna move on. Let's move on. All right.
Sir, could you just show the question again? I think somebody was asking to
okay, the question again. There you go. There you go. All right, there you go. All right, so since some of you got that one wrong, I'm going to give you a second chance, all right, to have a go at this one, all right? How many moles are contained in 64 grams of oxygen gas? 64 grams of oxygen gas. Now remember, oxygen, I'm going to give you the relative atomic mass of oxygen. The relative atomic mass of oxygen is 16. Relative atomic mass of oxygen is 16. All right, let's see what you're saying about this one.
Okay, so I'm seeing 2 moles, 4 moles, 2 moles. Not sure what that is. 0.5. 2.
All right.
1.68.
1.68. Very interesting.
Very interesting. All right. I'm seeing 4 moles. So again, there's.
Yes. All right. So it's making the same error, guys. Remember, oxygen is a diatomic gas. So it exists as diatomic molecules. Yes. So it exists as O2. Right? O2. So let me see the answers improve now, quickly.
2, 8. 2, 3.
Come on, guys.
0.5. 0.5. 0.5.
All right.
All right. So take it through again, sir.
All right. So I'm gonna do it right here on this board. I want you to look at the one that you have in front of you. The example that you have in front of you. Oxygen. Oxygen is O2. O2. You know what? Let me just clear this. All right. Oxygen is O2. All right. That's what oxygen exists as. So if O is equal to 16, then O2 would have mass 2 times 16, right? Which would be 32. So its molar mass would be equal to 32 grams per mole. So 1 mole of oxygen will weigh 32 grams. Are the answers coming in any better now?
So I'm seeing 64 divided by 32 equals 2 moles.
Right.
2 moles.
Yes.
So
the
see,
question.
I'm seeing some 2, yeah, 2 moles.
All right. So look at it, guys. Now it says how many moles. Right. So we don't know the moles, and it's giving us the mass. All right. The mass is 64 grams. So we're saying that if we have 64 grams, then X mole, because we don't know how many mole, that would be X mole of oxygen. Yes? So X over 1 would be equal to 64 over 32. X over 1 would be 64 over 32, which would be equal to 2. And we must put our units, 2 mole. All right, so congratulations to all who got that correct. Very good. And those of you who tried, you'll get one last chance. You get one last chance, and I promise you that I'm coming to that very shortly. All right. So then, guys, we would just establish a relationship between the mole and number of particles, as well as the mole and mass. All right. And there's also a relationship between the mole and gas volumes. The mole and gas volumes. So the picture that you get, right, so I don't know if we have a lot of time to go into the whole theory, but basically, Avogadro established that volumes of gases is proportional to numbers of particles, which is proportional to moles. So volumes is also proportional to moles of gases. All right, so you must know your Avogadro's law. As you're seeing in front of you, you must know this to be able to write it out and understand what it means. Now, if volume is proportional to moles, what that means is that 1 mole of a gas will have a fixed volume under given conditions of temperature and pressure. All right? Now, so that is where the idea of molar volume comes from. Right?
Somebody wants you to go back?
Go back. To where?
To the answer. So that must be the oxygen one then. To the answer. Just to the answer. They probably just show the okay, you can do a quick screenshot. So this is X over 1. All right, just doing ratios from here. I cross multiply before. Even if you prefer to say, if you're comfortable with cross multiply, then that's fine. And either way, you get the same answer. It doesn't matter. All right. All right. So that must be enough time there. So what I'm doing here, I'm summarizing the relationships that we've looked at so far, right? The mole is a central way in chemistry in which we measure amount. There are different ways of measuring amounts. You can measure amounts by doing a mass, right? So if I go to the market and I'm going to buy yams, they're going to weigh it, all right? They're going to sell me by the kilogram or by the pound, right? That's one way of measuring amounts, right? If I go to the market and I'm going to buy oranges, they're going to sell me by the dozen. Count the items. The mole allows you to count particles through Avogadro's constant. So 1 mole contains Avogadro's constant number of particles, right? The mass of 1 mole is the molar mass. This is how I wanted to study mole. Understand relationships. And then 1 mole of a gas has a particular volume under certain conditions of temperature and pressure. That's molar volume. All right? Right? Write in the chat, what is molar volume at RTP and STP? Okay, so I'm seeing 24 dm cube. And SCP, I'm seeing 22.4. Somebody said 2.24.
Whoops.
20. Somebody says 22.5. Anyway, 22.4 STP, 24 dm cube.
RTP.
Mm-hmm.
All All right, good. All right, good. So I think we have an idea. So 1 mole has a particular volume. 1 mole of any gas has a particular volume at RTP. Now, I don't worry about it. I'm going to switch now and start doing some questions because I realize the time is kind of going. So I'm going to do a couple of questions. We really have to do a couple of questions. So I have some questions here which I have together, and we're going to start going with. I'm going to give you a chance, a minute, for you to try this one. This first two here. It has a long preamble, so you can read through it. It says, in the 16th century, I hope you can see it. Yes, I think you should be able to see that. In the 16th century, a large deposit of graphite was discovered in the Lake District. People at the time thought the graphite was a form of lead. Nowadays, graphite is used in pencils, but it is still referred to as lead pencil. We call it in Jamaica, right? A student decided to investigate the number of carbon atoms in lead pencil. He found that the mass of the lead pencil was 0.321 grams. Calculate the amount in mole of carbon atoms present in the student's lead pencil. Assume that the pencil is pure graphite. All right, and I'm going to tell you that carbon, the relative atomic mass of carbon is 12. All right, or the molar mass is 12 grams per mole. That's saying the same thing. All right, so as soon as you can tell me the number of moles, type it in the chat.
Okay, so I'm seeing 0.026, 0.027, 0.02675, 0.027 moles.
Excellent. So some people are on the ball, right? So basically they gave you mass and they're asking you about mole. So we know that what links mass to mole? Molar mass, yeah? Molar mass. And we're given that for carbon. So 1 mole of carbon, yes, has mass 12 grams, right? So if we have 0.321 grams, then that would be X mole, all right? And then so X will be 0.321 over 12, all right? And so some of you are getting very precise answers. So you should be getting 0.02675. I'm writing the precise answer. So some people would have rounded off to 0.27. That's okay, I think, 3 decimal places. All right, more. Okay, good, yes. And what about anybody ready with part 2? It says, using Avogadro's constant, calculate the number of carbon atoms in the student's lead pencil. Who's really sharp? Let's go.
So I am seeing 1.61 times 10 to the 22nd power, but that's all I have so far. (1.6 times 10 to the 22nd power. Mr. Miller, hope I haven't lost you again. Okay. Okay, we have lost Ms. Miller again. So you should have calculated that by multiplying the number of moles by Avogadro's number.
So yeah, so there's a lot of guidance there. They tell you that you need Avogadro's constant, basically. All right, so 1 mole of C, we know, is 6.02, right, times 10 to the 23, and carbon atoms, yeah? All right, and we know that we had 0.02675 moles. So therefore, if we have 0.02675 moles, oh, bear with me a little bit here. It's not so easy to write with the mouse. All right, so if we have 0.02675 moles, we just multiply that, right? We can get X, right? So X would be 0.02675 times Avogadro's constant, all right? And we're getting what you're supposed to be getting, 1.61. So the answer is 1.61 times 10 to the 22 atoms. All right? All right, it says number of atoms there already, so I don't have to put atoms, but yeah. That's what you should be getting. Any puzzles? Anybody puzzled about something?
No, got it.
Okay, I'm seeing no
Right.
at this point. Please remember, if you have a comment or question, to raise your hand, all right? Or somebody's asking, when do you round off?
All right. All right, now that's a good question. It depends on how long the calculation is, right? And you can also take a guidance from the number of decimal places that you're given in the question. So for example, so this gives you 3 decimal places. So that's a rough guide as to how many decimal places you might want to use, all right? Or how many, I don't want to delve into significant figures, but it does give you a guide as to how far you want to go when you're rounding off. You don't round off for a long calculation earlier. So if you're doing a long calculation, right, or a calculation that connects going far down, you don't want to round off too early, all right? All right, speaking of rounding off, right, this next set of questions, I'm not going to go back to theory. I'm just going to do questions and theory within questions from now on. All right, so speaking of rounding off, here's a question that has to do with the mole and chemical formulae. Now, I'll do just this small amount of theory before I go into this, right? All right, so when we write the formula of a compound, what are we saying? Suppose I write, the formula of sulfuric acid is H2SO4. What does that mean? What's that telling me? Write it in the chat for me. What is that telling me?
Waiting on the responses. Has 2 mole of hydrogen.
Mm-hmm.
2 hydrogen atoms per sulfate molecule.
Mm-hmm.
Telling the compound composition.
Okay.
You have 2 hydrogen, 1 sulfur, and 4 oxygen.
Okay. All right. So this is what we call the molecular formula of the sulfuric acid, right? And it gives the actual number of atoms of each element in 1 molecule of the substance. So what this is saying is that 1 molecule of sulfuric acid has 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen. Now, I made this worksheet. I use this worksheet because I know I teach all the empirical and molecular formula, but I know that empirical formula is not on the CSEC syllabus. So I won't spend a lot of time in actually doing this question, but I think it's very important that you understand what formula means, at least the molecular formula, all right? So molecular formula gives us the actual number of each atom present in one molecule or formula unit of the compound, all right? So I'm not gonna go on that, I'm gonna spend much time on that at all. I want to introduce that to you. Probably the most likely thing for you to get on the CSEC exam, apart from what we did first, are these questions that link the mole to equations. And this is where I want to spend a little bit of time about wrapping up moles. I want to do a couple questions with the mole and equations. All right, so let's go into this real quickly. I don't have, but before I go there, I just want to do a quick little theory wrap up. All right, so listen, when I write an equation like this one, magnesium plus oxygen gives me magnesium oxide. That's a solid, that's a gas, that's a solid. When I write that, and I balance the equation, what kind of information is that telling me? Well, it's telling me what elements are reacting, and it's telling me what are products, or what substances are reacting, what are the products. It's giving me states, right, for each of these terms. But it's also giving me, most importantly, for this part, what we're doing anyway, the quantitative ratios in which these reactants combine to form, in this case, just one product, right? So it's critical that we understand that, right? Now, one of the easiest ratio that you can write down is the mole ratio. What is this telling me? Write that in your chat. In terms of moles, what is it telling me about the amount of reactants and products in terms of moles? What is this equation telling me?
I'm seeing 2 to 1. 2 to 1. Do you want a more specific answer than 2 to 1?
Yes, ma'am. Talk to me.
2 moles Mg reacts with 1 mole of, I think that's oxygen. 2 moles of, and reacts with 1 mole of oxygen.
All right, so people are saying that 2 mole, this is saying that 2 moles of magnesium reacts with 1 mole of oxygen. And that produces 2 moles of magnesium oxide. Is that what people are saying?
I don't think, well, a few mentioned the oxide, but some persons didn't reach that far, right?
All right. All right. Now, since we know that the mole is linked to the mass via molar mass, perhaps we could write a mass ratio. We have here a mole ratio. Maybe we could write a mass ratio. Anybody can help me with the mass ratio? What would be the mass ratio?
Okay, waiting on the responses.
All right.
Mass ratio, write the mass ratio in the chat. "48 grams of magnesium reacts with 32 grams of oxygen to form 80 grams of MgO. That's one answer.
All right, somebody sharp. Magnesium is 24 and oxygen is 16.
Yes, somebody's saying 48 to 32 to 80.
Yes, 48. If we use the molar masses, we could say this is 48 grams because that's what 2 mole is. And 1 mole of oxygen, 2 times 16, that's 32 grams. Yes. And somebody said that this was 80 grams.
Yes, I saw 80.
Yes, yes. Suppose, remember, you know, moles, mass, volumes of gases, all related. It's just different ways of measuring amount, right? That's all it is. It's just that the mole is the central way and we can convert moles to all the other ways. So what volume could we write? What volume could we write?
Not seeing an answer yet. Somebody's asking about simplifying the ratio. So I guess you can mention.
Yes, you could if you want.
Mm-hmm.
Yes, you could if you want.
Okay, so
But I leave it there because I want to
24.
make another point.
There's a 24 here, but they're not telling me what it's related.
24 what? 24 what? Could I put 48 dm cube here?
24 dm cube, and there's a, well, somebody says magnesium. Somebody says 2 cm cube. I'm sure that's
2 cm cube.
It's probably a mistake.
Right.
24 dm cube.
We can put 24 dm cube for, we can put 24 dm cube for what? We can put 24 dm cube for the oxygen, because that's the only gas. Avogadro's law only applies to gases, all right? So we can't put any mass, I can't put any volume for magnesium or magnesium oxide, all right, folks? We can put it for the gas, and this is at RTP. What is this telling me? What is the big picture telling me here? All these 2 moles of magnesium is the same thing as 48 grams, right? So I could just get, I could get a variety of relationships. This, for example, I could say, okay, this thing is telling me that 2 moles of magnesium gives me 1 mole of oxygen. I could also say it gives me 32 grams of oxygen. I could also say that 2 moles of magnesium reacts with 1 mole of oxygen. I could say it reacts with 32 grams of oxygen. I could say it reacts with 24 decimeter cube of oxygen at RTP. All of that is saying the same thing, all right? Right, how much magnesium oxide can I get from 2 moles of magnesium? 2 moles, or 80 grams, all right? All that. So I'm gonna ask you a question now. I'm gonna ask you a question. Suppose I reacted 3 moles, let me put it in a different color. Suppose I reacted 3 moles of Mg. How many moles of oxygen would I get? How many moles of oxygen would it take to react? In the chat, talk to me. Suppose I reacted 3 moles of magnesium. How many moles of oxygen would it take to react with that?
I'm seeing 2, 1.5, 2. Somebody wants to go back over why is only the oxygen has the volume. 1.5, 1.5. And somebody was really wanted you to go over everything. I think they joined late. Anyway, so 3, 1.5, 1.5. Yeah, that's what I'm seeing so far. 1.54.
All right. Okay, good. All right. So some people are getting it. The answer is 1.5 mole. Yes, 1.5 mole. And let's talk about. Somebody was asking a question.
Repeat the question and put the Mg beside the 3 moles, so they know you're asking about.
Yes.
Yeah.
Yes.
Right.
All right. So
they're
so
asking
let's
why oxygen alone has 24.
Okay, good. I wanted to answer that question. Yes. All right. So only oxygen has a volume because only oxygen is a gas. All right. So Avogadro's law and molar volume only applies to gases. Are we clear? All right. Everybody? Yes, good. So the question was, if I reacted 3 moles of magnesium completely, how many moles of oxygen would it take? All right. Now remember now, when I write this equation, folks, when I write this equation and I balance it, that equation is telling me that 2 moles of magnesium reacts with 1 mole of oxygen. It doesn't matter if it was yesterday, today, tomorrow, on Mars, or on Earth. 2 moles of magnesium is going to react with 1 mole of oxygen. 1 mole of oxygen weighs 32 grams. It occupies 24 dm cube at RTP. You get me? So I asked you for mole, right? I asked you for moles of oxygen. So what I would do from this now, how would I approach this problem? I would go to my equation and say, once I write my balance equation, I can write out my ratios like this. I say, all right, from my equation, magnesium to oxygen, that ratio is 2 to 1 in terms of mole. All right? So if I have 3 moles of this, then that would take X moles. So you see, 2 to 1. So the oxygen is half of the magnesium. Everybody see that? The mole of oxygen is half of the magnesium. So all you have to say is X must be half of 3 then. Talk to me, man.
So students, if you want to ask a question directly, you can raise your hand.
All right, so 1.5 mole then.
All right, Sir Miller.
Mm-hmm.
All right, just take them back through the equation, show them how you balanced it, and bring it back down to the ratios, because I think some persons are still.
All right, okay, all right, let's go.
Last time.
All right, let's go. All right, so I asked you, okay, suppose magnesium reacts with oxygen. I'm gonna write the equation for magnesium and oxygen. Now, you should know magnesium burns with oxygen to give the oxide, yeah? All right, so let's take it from basic. Let's take it from basic, all right? So magnesium is a solid, oxygen is O2 gas, all right? Magnesium oxide is MgO. We know that because magnesium is in group 2, its valence is 2, oxygen is in group 6, its valence is 2, so the formula will be MgO. All right? So MgO. We then balance the equation now. And when we look at this, we see that Mg over here, so just 1 atom, Mg over here, so 1 atom. That look good. But if we look at the oxygen, we have 2 here, and we have 1 here. So we have to put a number in front of the formula. Now we can't put it beside or in between, right? Has to be in front. So we put 2 there. Right now, when we put 2 there, we have 2 oxygen, but now we have 2 Mg. So we put 2 over here, so, and we balance the Mg. So now we balance our equation. Now, once we balance our equation, we're saying that, look, 2 Mg atoms give you 2 MgO formula units, yeah? But remember now, particles, number of particles is proportional to moles. So as much as this is a particle ratio, it's also a mole ratio, right? So these numbers, we have some big word if you call them. The number in front of the formula, some people have big numbers, stoichiometric coefficients. Don't worry about that. It's just the numbers that we use to balance them, right? And if there's no number there, the number is 1, right? So this is telling us that 2 moles of magnesium, this number here, react with 1 mole. If there's no number there, the number is 1. 1 mole of oxygen to give you 2 moles of MgO. Yeah? Now, because we know the molar mass of these elements here, we can also work out a mole ratio. We can already work out a mass ratio, because we know that 1 mole of magnesium is 24 grams. If we have 2 moles, it's 48 grams. Yeah? Oxygen is O2. 2 times 16 is 32. Right? So that's 32 grams. O2 is 32 grams. Talk to me. 1 mole of it. MgO, Mg is 24 plus 16 for oxygen, that's 40. But it's 2 of them, 2 moles. So 2 times 40 give us 80. All right? So that's 80 grams. All right? And then we can write a volume ratio too for the things that are gases, because gases have a particular volume under certain conditions like RTP and STP. At RTP, we know that 1 mole of any gas is 24 dm cubed, and is 1 mole of oxygen we say reacting here. So that is 24 dm cubed. Now I ask the question, if I have 3 moles of magnesium here, so now, yeah? Instead of 2, suppose I reacted 3 moles of magnesium. How much oxygen would it take to react? That was the question, right? And we are saying that since I know that this is the law, right? These ratios are the law for when magnesium reacts with oxygen. It can't change, all right? Magnesium reacts with oxygen in a 2 to 1 mole ratio. So 2 moles of magnesium react with 1 mole of oxygen. So if I have 3 moles of magnesium, it's going to take half the amount, because it's half the amount of oxygen react with in terms of moles. In terms of moles, if you have 2 moles of magnesium, 1 mole of oxygen. If you had 1 mole of magnesium, half mole of oxygen. If you have 3 moles of magnesium, half of that, which is 1.5. All right?
Sir. All right.
All right. So let me ask you one little question before we do another question now. Let me ask you one little question. Let me just ask you one little question. One little question. Suppose I have 96 grams of magnesium reacting, right? What mass of magnesium oxide would I get? Suppose I react 96 grams of magnesium in oxygen, right? What mass of magnesium oxide would I get? Somebody's writing in the chat.
Okay, so 48, 64, 98 grams of MgO, 48. Okay, so remember you're asking about the mass of magnesium oxide. So I see 96, 64, 96 MgO.
Somebody must get it, and not stop it.
We believe 160. Yes, I'm seeing 160 now. 160.
160.
Yes, 160. All right, so I'm seeing the 160s coming in. So I think you're saved, sir. You're saved.
I'm saved.
Yes, you're saved.
All
right. So you're gonna have to show them how they get the 160. Yeah.
Right. So I'm gonna have to show some people, right? How we get the 160. All right. All right. Yes. All right. So let me extend this out. Let us extend this out here to the magnesium oxide. Yeah. Now, look at the ratio. Since they give us mass, we can use the mass ratio, man. So we have mass ratio here now. The mass ratio said 48 grams of magnesium. Give me 80 grams of magnesium oxide. That's all. On Mars, on Earth, yesterday, tomorrow, any time of the day. Anytime I burn 48 grams of magnesium in oxygen, I am going to get 80 grams. This is why we work out all them ratios here. Talk to me. Huh? Yes, man. So let's look at this now. 96. What is the relationship between 96 and 48? Anybody see I double the amount of magnesium? Anybody see that?
Yes, there's a
Yes, man. All I did was double the amount of magnesium. So what I'm going to do? I'm going to form double the amount of magnesium oxide.
I saw somebody adding 48, 32, and 80. I'm not sure.
48, 32, and 80.
I mean, adding it, but that's not the way to get it.
Correct by coincidence. Oh my God. Actually, you could argue that out, but I doubt you know how to argue it out. but you're correct by coincidence. Yes. So the answer is 160, folks, because all you have to do, you don't have to go to moles because you're given mass and you already have written in front of you a mass ratio of 48 to 80. So as long as you know that you're using the mass ratio, 48 to 80, right, then 96 would give you twice the 80, right? 160. So I'm going to do it that way. I'm going to show you another way because a lot of you would probably want to use the moles, and probably one or two of you are confusing it with the mole. So I'm going to do it both ways. So here's how you would do it, yeah? Using the mass only. So I would say, okay, from my equation, magnesium in terms of mass to magnesium oxide, right, is in terms of mass, this is 48 grams, then this is 80 grams. So if this is 96, then obviously this will be, 96 is twice 48, yeah? So that would be just twice 80, which is 180, which is 160, right? Or if you want to work it out on your calculator, lots of you love your calculator, right? I know that. 96 over 48. So you should be getting 160, right? 160. Right? So your answer should be 160. Now, I know some of you are confusing with the moles, yeah? So I want to just do that. I want to do it that way. So some of you are writing that off. I'm giving you 10 more seconds because I want to do it with the moles. Because I know some of you might be saying, why not work in moles? Working in moles just waste your time, right? Because you could say 96 grams is how much moles, and then 2 moles give you 2 moles, and then you find the moles of MgO, then convert the moles back to grams. It's just a waste of time, all right? So, you know what? I'm not going to even bother to do that. But I'll reason it out for you. I don't want to do all that calculation. All right? All right. Okay, so I'm gonna rub this out now. I'm gonna show you right here. All right, so I could have done it with moles like this. Let me show you. I could have done it with moles. All right, it's gonna take a little bit more time. All right, so
there's a raised hand. Just give me a sec.
Yeah, go ahead. Go ahead.
Yes, go ahead, comments.
You doubled the magnesium because it has 2 moles instead of 2. So why didn't you double the magnesium oxide?
Well, that's exactly what we did. We doubled the magnesium oxide, but we used the mass ratio. So we doubled the magnesium, which is 48 to 96. So the answer was double 80, which is 160.
But so it was 96 to 160.
Yeah, the question was that if I burn 96 grams of magnesium, how much magnesium oxide would I get? So the equation tells me that when I burn 48 magnesium, I get 80 magnesium oxide. So if I burn
Yes.
96, which is twice the amount in the equation, then I'll get twice the amount of magnesium oxide.
So it would be 96 to 160.
Right. Right. It's the same ratio. 48 is to 80, then 96 is to 160. It's exactly what we're saying.
And
All right.
that's it. It's the
Yeah, that's it.
160.
Yeah, 160 is the answer.
Okay.
Yeah. Not
Sir,
complicated. Yes, go ahead.
just a quick question. What if you never had the 48 and the 80 to determine the 96? How would
All
you
right.
work it?
All right. So, all right. So suppose we never had the 48 and the 80. All right. So let's rub out all that then. Let's rub this all out and say, all right, okay. I did not have the 40 and I didn't have all that. Okay, let's go. I didn't have all that. All right. Didn't have all that. Yeah? I'd still have to be able to work this out, right? Once you balance the equation. Okay, so suppose I had the 96 grams of magnesium. All right, so the first thing I would have to do is, since I have the mole ratio, I would have to convert this magnesium to moles. All right? So I would go, all right, 1 mole of, I go, okay, let's work over here. I go, okay, 1 mole of Mg is 24 grams. All right? I wish I could write this a little better. All right, so 1 mole, right? 1 mole of Mg, right, is 24 grams. So if I have 96 grams, I would have to convert that to moles, eh? X mole. All right, so X would be equal to 96 times 1 over 24. Yeah? If we cross multiply.
Sir, excuse me.
Yes?
Are you still working out the question? Or this is a different one?
Yes. Same question. So X would be 4 mole. Are you with me? All right, so I've just determined that 96 grams of magnesium is actually 4 moles. So I am actually reacting 4 moles. Now, 2 moles of magnesium gives me 2 moles of MgO. So 4 moles is going to give me how much? Write that in the chat box quickly. 4 moles is going to give me how many moles of magnesium oxide? Dr. Campbell, what are they saying?
I'm seeing 8 and there's a 4, and quite a few 4s.
All right. So
And somebody has 8. Yes.
All right.
Sir, I'm not getting what you're saying.
All right. So do you understand how I got 4 here?
Yes, sir. We divide the
Okay,
96 by 24.
Okay, all right. Yeah. So what I'm saying is that if 2 moles of Mg gives you 2 moles of MgO, then how much would 4 moles of Mg give you? So if 2 is to 2, what would 4 be to what?
Sir,
4 would
4?
be to 4. Yeah, man. 4 would be to 4, man. Yeah, man. Yeah, man. 2 is to 2, 4 is to 4. Yeah? The same. Yeah? So
Yes.
that would mean that we have 4 moles of magnesium oxide. Right? So therefore, we have 4 moles of MgO. But the question was what was the mass that would be produced? Right? But we can work out the molar mass of this, right? Because Mg is 24 and oxygen is 16. So the molar mass would be 24 plus 16, which would be equal to 40 grams. 40 grams. So guess what? 1 mole of MgO, right, is 40 grams. All right? But we just work out that 4 moles of MgO we're going to form. So if we have 4 moles of MgO, then that would be X grams. Yeah? Talk to me. So X no 160, man. X no 4 times 40. Same 160. It's the only thing is that we go around one whole heap of corner, down the road, around the town, and come back to the same thing. Talk to me.
Yes, 160 in the chat.
All right, good, good. All right. Listen, man, it's 4 o'clock, you know, and we don't touch electrolysis yet, you know. All right.
Yes,
I'm
sir.
going to do one more. I want to
Yes.
do I want to do a question on moles, actual question. All right.
Right. Do that and then you start electrolysis.
All right. All right. Good,
Right.
good. All right. All right. Let's do this one. This is an interesting one. All right. Let's see. Yes. Have volume in there. Good. All right. Good. All right. So let's read this question now. Work with me now. Put your answers in the chat. All right. I'm going to give you some things before we start. Carbon. You can go and read. Carbon is 12. All right. Carbon is 12. Calcium is 40. You should have your periodic table with you. Come to chemistry class, you must have your periodic table. Oxygen is 16. All right. Let's go. All right, so it says calcium and its compounds have typical group 2, are typical of group 2 elements in the periodic table. Calcium carbonate reacts with acids such as nitric acid, and they give you the equation for the reaction here, and they tell you that a student neutralized 2.68 grams of calcium carbonate with 2.5 mole per dm cube nitric acid. The equation for this reaction is shown below. So let's look at the essential information, the quantitative information. Student neutralized 2.68 grams of calcium carbonate with 2.5 mole per dm cube nitric acid. And they give you the equation. All right? And they will give you these masses too. All right? So the first part of the question says, part 1 says, determine the amount in moles of calcium carbonate that reacted. So they give you the mass. All right? And I said that you can work out the molar mass of this calcium carbonate. Can we work out the molar mass of calcium carbonate? Calcium is 40. Talk to me. Carbon is 12. All right, and oxygen is 16, but we have 3 oxygen atoms there. So what's the total you're getting in the chat there?
I'm seeing 100, a few hundreds.
All right.
Hundreds.
100 grams per mole. All right, excellent. All right, so we have the molar mass. So how are we going to get the moles now, guys? Anybody have the answer for the moles? Determine the moles of calcium carbonate reacting.
Somebody says divide.
Divide what by what?
Molar mass
2.5 by 100.
RMM.
RMM by the molar mass. What? To me.
All right, somebody is giving the answer, 0.0268, and another person has 0.268 moles. 2.68 divided by 100, 0.0268, 0.0268 moles.
So guys, we just worked out that 1 mole of calcium carbonate, right, is 100 grams. That's what we just worked out, you know. Yes? So now we're told that we have 2.68 grams. If we have 2.68 grams, Yes. The question is, how many moles is that? Right? So X will be equal to 2.68. Yes, divide by 100. Somebody had that. And that would be equal to, move your decimal places 2 places to the left. You're dividing by 100. 2.0268 mole. All right? And those for people who love the formula, 2.68 was the given mass. All right? I know some of you love your formula. And 100 was the molar mass. Yeah? You love your formula, and X is the mole that we were trying to calculate. No, sir? Yes, mole equal given mass over molar mass. All right, remember I tell you, use relationships and you can work out formula from that. So I just work out the formula. All right. All right. If you just remember, say we're dealing with mass and mole, that's what we deal with molar mass. Write down the molar mass. That's a relationship. 1 mole of calcium carbonate is 100 grams. And then look at the question now. What does it give me? It gives me grams. What is it asking me? Moles. Make sure so you have moles on one side and mass on the other side. So whatever you have on the left-hand side, make sure it's consistent, the same. If you mix them up, you have problems. All right, so we have the number of moles, don't we? All right, so we have the number of moles of calcium carbonate. Now, remember, we also have our equation. And our equation is telling us that there's a certain ratio going on. What is the ratio, folks? 1 mole to 2 moles to 1 mole to 1 mole to 1 mole. All right? All right, stay with me now. Now it says, calculate the volume in centimeter cubed of carbon dioxide produced at room temperature and pressure. All right? All right, guys, let me see. Let me give you a chance. Let me give you a chance. I don't want to rush you. I'll give you a chance. Try to get this correct. Talk to me.
No responses yet?
Yes, I think they'll take a little while with this one. So the first thing you want to do, you want to work from your equation. What's the mole ratio here? How does volume come into it? What's the unit for volume? What are the conditions? All right.
Okay, so there's a 643.2 cm cube, question sign.
Not confident. Not confident? Man, you should be confident, man.
Right. 643.2.
Another 643.2. All right, let's just scroll back up. We can see the equation.
0.6432 dm cube.
Yes, interesting. All right. Very good. All right, so let's see if we can work that out then. The key thing is we have to use the relationship because we just worked out the moles of calcium carbonate that reacted, eh? And so we have to use that to determine how much CO2 would be actually produced from this thing here. So let's change the color of my ink here. Let's go red. All right, so let's look at it. So from my equation here, I can see that there's, for every mole of calcium carbonate that reacts, I actually get 1 mole of carbon dioxide, don't I? Right? That's what I can see, right? And so it's a very easy write-up because then if I have 0.0268 moles of that, then won't it give me the same number of moles of CO2? Yes, man. Yes, man. Yes, man. Yes, man. And guess what? 1 mole is what volume? 1 mole is what volume? So guess what? Let's write it out down here. Let's write it out here. So 1 mole of calcium. Oh, let's write that properly. Sorry about that. Yeah. Yes, yes, yes. Let's write it good. All right. So 1 mole. 1 mole. Yes, let's get it properly. Of calcium carbonate from my equation gives me 1 mole of CO2. 1 mole of CO2. Not true? Yes, man. Look a reason, man. Look a reason. So guess what? The question really asked me volume of CO2, and it asked me volume in centimeter cube. So guess what now? I can go around long corner, or I can just reason to the chase, cut to the chase, all right? Because I can then say, all right, 1 mole of CO2, what is the volume of that? According to molar volume. That is the same thing as, talk to me, people. 1 mole of calcium carbonate. Give me that. So 1 moles of calcium carbonate is what volume? 24 dm cube, right? But the question asked me for centimeter cube. So I can just write
1 mole of CO2, 1 mole of CO2, sir. Not calcium carbonate.
Sorry, 1 mole of CO2. I'm sleeping, folks. 24,000 centimeter cube of CO2, right? Everybody understand the little step that I just took a while ago? How 1 mole is the same thing as 24 dm cube. And 24 dm cube is 24,000 cm cube. So 1 mole of...
I'm sure you're going to be asked how you get a 24,000. So you can just scribble it somewhere.
Right. So folks, remember me now. 1 decimeter cubed, right, is equal to 1,000 centimeter cubed. Yes, yes, yes. You have to be able to do this conversion. They're not going to tell you, and they're going to test it. Right? So you must know your conversion. 1,000 cm cube make 1 dm cube. 1,000 dm cube make 1 meter cube. 1 million centimeter cube make 1 meter cube. Right? Get your timetables out. Right? Make sure you know that. All right? So we have established the equivalency then. 1 mole of calcium carbonate give me 24,000 centimeter cube of carbon dioxide. Because we know that 1 mole of CO2 has volume 24 decimeter cube. Yeah? Yes, man. Yes. So now, if I have 0.0268 moles of this, then that would give me X cm cube of carbon dioxide. I almost said calcium carbonate again. All right? So X is just going to be equal to, if we cross 0.0268 times 24,000. And so that first answer was correct. Who was that? Very, very good. 643.2 centimeter cubed. All right? Yes, yes, yes. Talk to me.
Yes, sir.
All right. Everybody take a screenshot if you don't get it. I know some people, you want to work out the moles of CO2 first and then convert that to volume. No problem. Right? But you can reason it out just like that because 1 mole is 24 dm cube. So you can say 1 mole of CO2 is therefore 24,000 cm cube. Yeah? All right, good. So 643.2, folks. All right, so let's talk about electrolysis then. Let me go back. Let me just people give it one last chance. all right, now with electrolysis now, I want to see what route am I going to take here now. Because guess what? The time is up on us now. Do we try to?
We can get some extra
We
time.
try to go too far.
We can get some extra time, so
Okay.
let's see how far we can go.
Okay.
Or somebody wants to snap the entire question, so could you just go back up a bit?
Okay, all right. So let's go. All right, let's see. Let's do bam, bam, bam. Make it easier for you. There you go.
Sir, go back up to the top.
Up to the top. No, that's the top, isn't it?
No, we're not there yet.
Top of question 5. You're not seeing it. You're not seeing 5 at the top.
No, we're not seeing where it started. Not seeing where it started.
Let me new share that. All right, are you seeing it now?
No, sir, we're still seeing 2.
We're not seeing the first part.
You're not seeing calcium and its compounds?
No, sir.
No.
All right, I'm going to stop sharing.
Right.
Stop sharing. All right. Better
Yes,
now?
sir. Yes, sir.
Okay.
All right,
All
good.
right.
All right, so let's see what we can do here now. Ooh, let's go. All right, so we looked after that, moles and electrolysis, moles. All right, let's see if we're gonna try, let's see if we can get, let's see if we can run through as much of the concept as we can. The qualitative bit, and then we'll do the quantitative bit as we hit the question, all right? Let's do, so you should be seeing are you seeing electrolysis with Mr. Miller in front of you?
Yes.
All right, good. All right. Yeah, so I'm not gonna go to, I'm gonna start with the basics with conduction. You should know about conductivity and the basic experiment to test if something conducts electricity. All right, that you ought to know, and some of the common materials that are good conductors, some of the common ones that are insulators. All right, so I'm expecting you to know that out of just your knowledge that you would have come up with through the system at this point. At this point, you should know the common conducting materials and the common insulating materials. All right. So in front of you are some terms here. All right. Let's start with this thing, electrolysis. Let's start with those terms. We want to make sense of these terms. Electrolysis. The term lysis means breakdown. Yeah. So when we see electrolysis, what we really mean is that we're breaking down something using electricity. Yeah, using an electric current. So that's the first thing you need to understand what we're doing. That's what we're doing when we're looking at electrolysis. We're using electricity to break down a compound. That compound, right, is what we call an electrolyte. And that compound is something that conducts electricity, a liquid that conducts electricity. By definition, an electrolyte is a liquid that conducts electricity. And you ought to know by now examples of such liquids. So such liquids would be your ionic salts, like a sodium chloride, magnesium sulfate, etc. All right, as well as molten ionic substances. And by molten, we mean melted, right? Melted. You also have things like your acids and your bases, your dissolved acids and bases. Those also conduct electricity. Those are liquids that conduct electricity and are broken down, therefore, bypassing an electric current through them. All right. Now, so in electrolysis, therefore, basically what we're doing is that we're setting up a solution, a liquid. And let me not just say solution, liquid, and we're passing current through the liquid. And we're using what we call two contacts that we call electrodes. One of them is positive, one of them is negative. This I expect you to know. So in front of you, you're looking at a diagram for the electrolysis of molten lead 2 bromide. Now, molten lead 2 bromide, name suggests melted lead 2 bromide. Now, this electrolysis is electrolysis in the simplest case because you only have one cation and one anion. So it's an ionic salt, a molten ionic salt. That's the easiest case to look at in electrolysis. Because guess what? Because you only have one anion and one cation, then your products, what you're going to get are very, very clear. You have no options to think about. All right? Okay. Now let's talk about the setup. All right? So you have 2 electrodes. Now we have 2 types of electrodes that we use. We have what we call inert electrodes or active electrodes. Inert electrodes don't take part in the reaction, they just carry the current. For that, we usually use carbon in the form of graphite, and platinum may also be used, but that's expensive, so people usually use carbon. All right, so we usually use carbon in the form of graphite. All right, now, the first thing that you have to know when you look at an electrolysis diagram like this, a circuit like this, is that you have to know what is positive, what's going to be the positive electrode, what's going to be the negative electrode. All right, and so you have to look at the battery or the power supply up here, okay? And the tall ones, the tall one is the positive one. So this one, tall one, that's to the furthest left, and the short one is the negative one. So this tall one is the positive, it's going to connect. So this one here is your positive electrode. All right, and here is your negative electrode. Okay, that's the first thing you ought to be able to pick out. All right, your positive electrode and your negative electrode. Okay, are we okay so far? All right. Now the electrodes are termed anode and cathode. Now, the anode is the electrode at which oxidation takes place. All right, and the cathode is the electrode where reduction takes place. All right. Now, in electrolysis, the anode is the positive terminal. All right. In electrolysis, I go at pains to say that because I'm a sixth form teacher, and when you do the opposite process to electrolysis, the anode has a different sign. So I'm just making sure that you understand that the anode being positive applies to electrolysis. Right? In this case. All right, so the electrode that's attached to the positive terminal is the anode, and the one that's attached to the negative terminal is the cathode. And it's easy to remember in terms of what ions go where. Anions go to anode, cations go to cathode. Simple to remember. All right? So you have to remember that. All right, I mentioned the electrodes already. All right, so let's look at this one now. Let's look at lead. We're saying that at the cathode, the cations are going to go there. That's the positive ion, the lead in this case. And it's going to go there, and it's going to get electrons. It's going to take on electrons, right? So lead 2+ ions take on 2 electrons and become discharged. So you take on as many electrons as you need to become a neutral atom, right? And lead 2+ obviously needs 2 electrons because each electron is -1 charge, right? So lead forms molten globules at the bottom of the crucible. We say that lead ions have been discharged. Make sense? So at the cathode, cations go there, they gain electrons and become discharged. All right, now let's look at what has happened on the anode. Now at the anode, guess what now? The anions go there. All right, in this case, you have the bromide ions. All right, each bromide ion takes on 1 electron, and you form 2 bromine atoms, which promptly come together to form a bromine molecule. Right? So because bromine exists as Br2, we don't write out the individual bromine atoms. We don't write out the discharge for the individual bromine atoms. We write it out as if 2 bromine come together to give you 2 bromine ions come together to give you a bromine molecule, and you lose 2 electrons. So each bromine atom loses 1, So if you have 2 bromine, you lose 2 electrons overall. All right? Now bromine in this state, remember now, this would be hot because molten, right? Melted, so the temperature has to be higher, right? So in this state, the bromine, which is normally a liquid, would be a gas. And bromine is a reddish brown gas, right? So near the anode where this is happening, you're going to see a reddish brown gas coming off. All right? So this is easy, man, because guess what? Electrolysis of molten ionic salts is easy. There's only one thing going to the cathode. There's only one thing going to the anode. All right? So pictorial, this is some pictures of what happens. Overall, lead bromide is becoming lead and bromine. So that's the overall chemical reaction that's achieved by passing the current through lead to bromide. We produce lead and bromine gas. All right, so lead ions move to the cathode, bromide ions move to the anode. All right, bromide ions give up electrons to the anode. The electrons travel over to the cathode. See them traveling over, yeah? And they add to the lead ions. The lead ions gain the electrons, and you get lead globules over at the anode, at the cathode, and bromine gas over at the anode. All right. Here's a little question for you. Answer in the chat quickly. Suppose I electrolyzed molten iron 3 chloride. What would be the color of the gaseous product? You're told that you get iron metal and a gas. What would be the color of the gaseous product? Answers in the chat. Talk to me.
1 sec. One sec. Okay, so I'm seeing C. I'm seeing a lot of C's.
Lots of yellowish green, right?
Yellow.
Chlorine, right? Excellent. Excellent. Yes. All right. All right. With reference to the previous question, at which electrode is the gas formed? Same, right? So this is the same question. This is the same iron 3 chloride. Which electrode would be the yellowish green gas formed?
Okay, so I'm seeing anode A, quite a few A's.
Excellent. So yes. So we know that the iron is cation Fe 3 plus would go to the cathode, and the chloride ion negative would go to the anode. Excellent. Now, where it becomes a little bit tricky now for you with electrolysis is when you have to electrolyze aqueous solutions. When you have to electrolyze aqueous solutions. Now, I have a diagram here, right, which can be a little bit deceptive, but is in general instructive because it shows a little setup to electrolyze an aqueous solution. And you see there's the electrolyte solution. You have the 2 electrodes, and you basically have 2 test tubes inverted over the electrodes. And that should give you the idea that you're going to get gases. And now this is usually the case, especially for dilute solutions. So why is this so? Why is it with dilute solutions we usually get gases and so on? We have to work out the details a little bit first. All right, so I'm going to skip down a little bit. Don't pay me any mind. I'm going to come back to that. I'm going to skip down a little bit. Now, let us expand out now. Because when we have these aqueous solutions, we have choice. Because once you have an aqueous solution, you're going to have more than one cation and more than one anion. You could have one cation, but you could have multiple choices as to what anion, what cation is going to be discharged at the various electrodes. All right. So for example, if I'm talking about dilute magnesium chloride solution. All right? Yes? I know that I'm going to have magnesium dissolved in water. That's going to have magnesium ions, and it's going to have chloride ions. Eh? I know I'm going to have chloride ions there. No? From the magnesium. Yeah, man. From the magnesium chloride. Yes. Yes. But it's dissolved in water, which also ionizes slightly to give hydrogen ions and hydroxide ions. No? So right there we have 2 cations and we have 2 anions. So we have to determine, here's the thing now. So when I am electrolyzing an aqueous solution, I have to be able to figure out, okay, what's going to happen here? I have hydrogen there at the cathode. I'm going to have magnesium there at the cathode. Which one is going to be discharged? Are both of them going to be discharged? All right. Same thing over the anode side. I'm going to have 2 anions. How do we decide what is discharged? All right. Anybody want to put any suggestions in the chat? How do we decide what is discharged?
So where it is in the series, where it is located in the series?
Yes, series. What series is that?
The reactivity series, sir.
Reactivity series. All right. Anybody have another series they want to tell me? Talk to me in the chat.
All right, so we're seeing position in electrochemical series.
Yes.
Electrochemical series. Electrochemical
All right.
series.
So reactivity series, good try, but remember now, it's slightly different from the electrochemical series. All right. So it's position in the electrochemical series. Yes. Yes. As well as 2 other factors that we're going to look at: concentration of the ions in the electrolyte and the type of electrode. Let's start with the easiest one, the type of electrode. Type of electrode, well, look, you have 2 types of electrode. You have inert and active. For the most part, most of the electrolysis that you are on your syllabus use inert electrodes. So the electrodes don't take part normally. The only time we use active electrodes is when we're doing electroplating or purification of metals like copper, okay? All right, so for the most part, you're going to be using inert electrodes, graphite or platinum. All right, is that clear? So that don't usually come into it, okay? All right, so the 2 major things are the position in the electrochemical series and the concentration. Now, if the concentration is low, so if it's a dilute solution, then concentration don't have no impact. It's only the position in the electrochemical series, all right? All right, so that's the main one. So you have to know your electrochemical series. You have to be able to position all your ions in your, you're gonna have to remember that, folks. That's not gonna be in your data booklet on your exam, all right? It's not gonna be there. You're gonna have to, there are many memes on the internet, right? Find one and make sure
sir, there's a raised hand. And
yes.
Remember, students and colleagues, please raise your hand if you have a question.
Yes, yes, go ahead.
Sir?
Yes, ma'am, go ahead.
I think I remembered my teacher saying something like, if it is an allergen, then it would be discharged as well.
All right, it's under what circumstances you're talking about, right? So you have to know exactly what circumstances you're talking about there, all right? And we look at the electrochemical series.
Somebody's asking, what's the difference between electrochemical and reactivity series?
All right, now, they are very similar because both of them tend to give you an idea of how easily metals give up electrons, all right? And that is usually a measure of how easily they react. But the reactivity series is determined by how easily the metal react with a set of substances like water, like acid, like oxygen, all right? While the electrochemical series is based on measurements called electrode potentials, all right? Which you don't know yet. You go to 6th form, you'll understand that, what that means. So that is why you have slight differences. But generally, if you look at it, they are along the same lines, okay?
There's one more raised hand. If you could just allow. Comments, go ahead.
Sir, you said that when it's diluted, when you're dealing with diluted solution, you do not use concentration, but the electrochemical series. Is that
Yes. So when you have a dilute solution, and you have inert electrodes, the only thing that determines whether you are discharged or not is the position in the electrochemical series. And the lower you are in the electrochemical series, the easier it is to be discharged. All right. So if we look at this series as you're looking at it in front of you, silver is more easily discharged than copper 2 plus, which is more easily discharged than H plus, and so on and so forth. And when you look at it, you'll see some similarities with the reactivity series. You'll see that the most reactive metals are up at the top, don't you? Generally speaking. All right. So there is some similarity. I think one of the main differences is that calcium is above sodium in the reactivity series, if I'm not mistaken. But yeah, there is a similarity there. There is a similarity. But the main thing for you to remember is these common ones. You have to remember this. And then over here, hydroxide is at the bottom for anions, right? It's lower than the halogens and it's lower than sulfate and nitrate. As long as you remember that, you're fine. All right? Because remember, you're going to be dealing with solutions, aqueous solutions, which will have hydroxide ions and H plus. The other important thing to remember here now, in your electrochemical series, is the position of hydrogen relative to everybody else, right? So only your jewelry metals, it's easy to remember this, only your jewelry metals are below hydrogen. What do you use for jewelry? Copper, silver, gold, platinum, the very, very unreactive metals. Okay? Yes? That's key to remember. All right? All the other metals that are in your syllabus are going to be above hydrogen. Now, what this also tells you is that metals below hydrogen here do not react with acids. All right? So like copper does not react with dilute acid, nor does silver. You can use your vinegar to clean your jewelry, right? It's safe. If it is not, and your jewelry turned black, you know that it was fake, all right? Okay, all right, folks, all right? And then over this here on the anion side, I want you to remember that hydroxide is at the bottom, all right? So as you go down, right, it's easier to discharge, all right? Very good. All right, so I'm gonna go back up now. We'll go back up. Let's look at some examples, yeah? Look at this example. What was this one? This is where I was. So if we look at this one now, dilute hydrochloric acid. Dilute hydrochloric acid has what ions now? Talk to me. HCl is gonna give me what? It's gonna give me H plus and Cl minus. And then water, because it's dissolved in water now, that's going to give me H plus and
oxygen,
hydroxide, right? Excellent. All right. So let's talk. All right. So at the cathode, we only have one choice then. So can we only have hydrogen ions at the cathode? So yeah, only hydrogen ions. So that's easy. At the anode, we'll have two choices. All right. So the cathode, we know we only have hydrogen. All right, so hydrogen is going to combine with the electron to give us H atom. All right, another hydrogen atom combines to give us H atom, but we know hydrogen exists as H2, so two atoms will combine to give us H2 molecules. All right, so we could have written 2H plus 2E equal H2. All right, so that's how you will see it on your thing, right? At the cathode, we're going to have 2H plus ions come together with 2 electrons to give us H2 gas. Yes? Yes, ma'am. Everybody cool with that? That's your cathodic reaction. All right. Well, the anode now, we have at the anode, we have the choice of chlorine or chloride or hydroxide being discharged. But based on our electrochemical series that we just studied a while ago, we know that hydroxide is at there. Hydroxide is at there.
Buffer.
All right, so hydroxide is going to be discharged. Now, here's one that you're going to have to swap, eh? All right, it's not nice to remember, but folks, you're just going to have to swap this half equation because chances are you're going to get it. All right, and you just have to remember it. All right, there's no easy way that I can tell you to work out this, that you're going to get this, that. Okay, no, just swap it. All right, this is the half equation for the discharge of hydroxide ions. 4 of them give up 4 electrons and you get water, 2 molecules of water and 1 molecule of oxygen. All right. So you know, if you do electrolysis, you know that that's one thing that you have to swap. All right. Yes, Tony Ann.
Sir,
Tony,
sir, I have learned, well, I'm not yet. Once it releases OH, once it discharges OH, it would have been 4 electron, 4E.
Mm-hmm. Yeah, man. That's it. That's what we're saying there. All right. Well, you have to know the half equation. You have to. All right. So let's see. Let's summarize what happens here now. So okay. Oh, okay. So what you're gonna find then? Look at this now. I want you to note this very, very carefully. So what you're gonna find is that at the negative electrode, that's a cathode, you're gonna get hydrogen gas. At the positive electrode, the anode, you're gonna get oxygen. But notice the amounts. Look at the amounts, folks. Do you see that the hydrogen is approximately twice the volume of the oxygen? Talk to me. Yes? It's approximately half. Note that. And let me go back and see.
Someone is asking to go over the cathode.
When you really cathode one. All right, let's go back up there. There's a cathode. That's cathode. All right. Yes. So the cathode, 2H plus 2E gives you H2. All right. That's what's going on there. All right. So let me explain why you have half the amount of oxygen as hydrogen. So at the cathode, we had what? 2H plus 2E, and that gave us H2 gas. At the anode, we had 4OH minus, gives us 2 water molecules. Sorry, give me 1 second. Yes, folks. So last thing, because I hear that we have to go now. We have to go now. All right. So if we look at this, we can see that when 4 electrons goes around in the circuit, we form 1 mole of oxygen. All right. 1 mole of oxygen. All right. Now we can see that it takes 2 electrons to give you 1 mole of hydrogen. So actually, if 4 electrons were used, if 4 electrons flowed, if we change this to 4, we would need to change this to 4. And then we would have 2 here. Yeah? So actually when 4 electrons flow here, we get 1 mole of oxygen and 2 moles of hydrogen. So we're always forming, when equivalent amount of electricity goes around in the circuit, we're always forming twice the amount of hydrogen as oxygen. All right. Yes, I think we have to.
Yeah. So we will have to organize, see if we can have a part 2 for the electrolysis. Sir Miller, you can let me know.
Okay.
All right.
I will try.
All right.
I'll try to do that because we haven't really done anything.
Yeah, we haven't started anything yet. All right. So so you're saying we have to go. All right.
Yeah, we have to go.
All right. So
our time is up.
Yes. All right. Thank you very much for participating in this session. Can we say our thanks to Master Teacher Miller for carrying us through moles and electrolysis? Come on, let me see those reactions. If you don't tell him how much you appreciate him, you won't get him back, you know. All right. So we thank you very much, Sir Miller, for taking us through the moles. And I know even doing the moles where we were just whetting the appetites because there's so much more to do. All right, so we want to thank Mr. Miller for all that he has done with us this afternoon. And as soon as we can arrange a second session to complete electrolysis, we will inform you via email, okay? All right, thank you, sir.
Okay, guys, we'll be with you. I hope you learned something, and we'll see you the next time what we can go through, okay?
Okay, all right. Thank you. We'll end this session. Thanks to everyone. All right, so persons were asking about how we'd get the recording. As I indicated, we're gonna post it to YouTube. It should have been live streamed. I'm not sure what happened. The ministry's YouTube channel is MOE Jamaica, one word. So you'll either see it on that or we will email the recording directly to your email addresses. All right, as well as send it to your teachers so you can get it from your teachers as well by the end of the day. All right, thanks again. Any last words, sir?
All right, see you next time.
All right, great. All right, thank you.